All right, we're taking a look at topic 9.10, electrolysis and Faraday's law guided notes. So this is our last topic for our mini unit here. So let's start off with electrolysis. This is, I'm just going to talk through your notes. I'm using my paper so I can show you guys the examples much easier and add things to our diagrams as we go. So electrolysis, not all redox reactions can happen on their own or are thermodynamically favorable, but we have the desire to make those reactions work. Sometimes we need a reaction to go in a particular way, and it's not favorable to do that, so we need to make it do it. So, for example, it is not favorable for water to split into hydrogen and oxygen molecules. So, what we can do is we can force that reaction to happen with energy. And this is called electrolysis, when we force a reaction, a particular redox reaction, to happen by adding energy to our system. So we're going to take a look at this hydrogen and oxygen example. We've got our water forming our H2 and our O2. We can determine the oxidation numbers to see the electron transfer. So hydrogen in a molecule is +1, oxygen's -2. On this side, they're in their elemental form, so they're both 0 oxidation number. So we can see that hydrogen is going down in charge. It's going from +1 to 0. So it is gaining electrons. So hydrogen is our redox reaction because it's going down in charge, so hydrogen, and our oxidation reaction would be the oxygen going up in charge. So oxygen is being oxidized and hydrogen is being reduced. Now, if we look at their standard reduction potentials, remember these are all reductions, oxygen has a higher value. So oxygen is better at being reduced. Okay, it has that higher value, it's better at being reduced. But we see up here that oxygen is being oxidized. So we can even calculate our E value for this reaction that we're given. Remember, it would be our cathode or our reduction minus our oxidation, our anode. So our reduction is hydrogen. So our hydrogen reaction is the second one, so negative 0.83. And we would subtract the 1.23 for oxidation. And what we get with that, negative 0.83 minus 1.23, is a negative value of negative 2.06 volts. So we can even see there that we are given that our E value is negative due to the reaction not being favorable. So it's another piece of evidence telling us this is not a favorable reaction. Number one, our oxygen would rather be reduced than oxidized, and two, when we find the value, it's negative. So not favorable, not thermodynamically favorable. So how do we force the oxygen to be oxidized when it wants to be reduced? And we do that by the use of batteries. Electrolysis can be done with the help of an outside energy source or a battery to pull the electrons from the oxygen and push the electrons to our hydrogen. Okay, so in this diagram, we've got our anode and cathode. Notice they're labeled here. They're both made of graphite, so like your pencil lead. So you can actually do this reaction with pencils if you shave them down. And they are in the same solution, so that's a little bit different. We're not in separate containers here with our half reactions. The battery is going to pull electrons from the anode side, attract the electrons or pull the electrons from the anode side, which pulls electrons from oxygen in the water surrounding it, turning it into oxygen or O2 gas. So if we look at this, our oxygen is on this side. So our electrode here, where it's coming in contact with the water, it's got electrons coming in here, and it's going to pull the electrons from our oxygen and pull them through the battery. Okay, so our positive side is attracting those negative electrons. And then the oxygen, now that it's lost its electrons, is going to hook up together because now they're just O, right, singular oxygens. They're going to hook up into pairs and we get O2 bubbling towards the top. So that's all our little bubbles is our oxygen gas bubbling towards the top. And then it pushes those electrons. So those electrons are going through our battery and it's going to push them into the cathode side, okay, our negative side. And again, it's surrounded by water. On this side, it's going to attract the hydrogen there, give those electrons to hydrogen. Hydrogen goes from being positive, it gains electrons, gets no charge, they hook up together and we get these little bubbles, and that's our hydrogen gas bubbling up, okay? So it pushes electrons in the cathode where the hydrogens get them and turn into H2 gas. So this setup and this experiment is really common. It's a common demonstration or experiment to do because it shows our volumes here of hydrogen and oxygen. Notice that hydrogen is about twice as much as oxygen. So it shows the chemical formula basically that we have H2O. We have twice as many hydrogen as we do oxygen. So it proves the formula and the balanced reaction for water, which is great. It's a good demo that's done in a lot of chemistry classes. So this is a nice example of when we use electrolysis. Okay, another great example of the use of electrolytic or electrolysis or electrolytic cells is rechargeable batteries. Okay, so when a favorable reaction occurs in a battery, it powers another device. So the battery is powering something else and we're using up that battery. So as mentioned in topic 9.9, the voltage will decrease over time as the chemicals in the cathode are used up. So we're using up that battery, right, where batteries eventually die. So to reverse this reaction, which is not favorable, right, it's going to want to go one direction, so we need to reverse it, go the other way. We use another energy source and recharge the battery. It reverses the reaction. The electrons flow in the opposite direction, causing the formation of ions in the cathode. Since the reaction is reversed, the anode and cathode, as well as the oxidation and reduction reactions, switch places. Okay, so in your favorable reaction, you might have, what's a good example of one? I'm trying to think one we've done before. But say your favorable has your oxidation and your reduction reactions. Your unfavorable reaction would have the oxidation becoming the reduction and the reduction becoming the oxidation, right? Because we're reversing the reaction. Okay, so they switch places essentially. That's how we recharge a battery. So every time your cell phone dies and you plug it into the wall, you're reversing the reaction in the lithium ion battery in your cell phone and recharging it, forcing that reaction to flow the opposite way so that when you unplug it, it can go in its natural, favorable direction. Okay, so that's really what's going on here with electrolysis. We call them electrolytic cells. That's another way, a name for them. So we've got galvanic and voltaic cells. Those are the favorable. Electrolytic cells would be unfavorable, and we have to use a battery to make them work. We have to use an outside energy source. So they're different than voltaic or galvanic cells because they require an outside source of energy. They do not require a salt bridge. And can take place in one container instead of two half cells. So you'll notice in this one, it does not have a salt bridge. Now what they often do, and you can see it labeled here, is they might acidify the solution or they might add salt into the solution, and that just facilitates the reaction, but it doesn't, it's not the same as our salt bridge, okay, because it's all in one container. They are both, so both types of cells, the same in terms of that oxidation always occurs at the anode. Reduction is still at the cathode. So when we switch places with things, our oxidation would be our anode, and it becomes reduction, and then it is the cathode. So those terms also flip because we're flipping the reaction. Okay. And the electrons will always flow from anode to cathode. All right. So from our anode to our cathode. And we saw that here as well. We started with our electrons here. The electrons were being taken from our oxygen, flowing through the battery, which was pushing them along, and then flowing into our cathode. So it's still going in the same direction, anode to cathode. We're just reversing that reaction. So while discussing electrolysis, or electrolytic cells, it's often important to discuss the number of electrons flowing because it deals with our calculations and how they determine the amount of product that can be formed from the reaction. A common thing that's done with this is things like electroplating. So if we want to plate something with a metal, we'll use electrolysis or electrolytic cells. So another example, in the figure here, we've got molten salt. So molten or melted sodium chloride is put through our electrolytic cell. The reaction produces chlorine gas and solid sodium, right? So we're producing the elemental forms of each of those chemicals, all right? So we're going from having a compound into the elements. So this is a common way we can separate compounds into their elements as well. So if we wanted to determine the amount of, say, sodium produced over a given period of time, we have the ability of doing that. So if we say, okay, here's our setup of our cell, it runs for 5 minutes, how much sodium is produced? How much solid sodium can we get from that? And we can actually do that calculation with a little help. Most of it is just conversions, so things we've done before. Not a lot of crazy new stuff, but there is a little bit of new stuff. So we have the equation I equals Q over T, which can help with this. So I represents the current, so the current flowing through our cell. So current is the movement of electric charge. So it's that movement of electric charge that it carries. So the movement of electrons or the movement of ions, that's called current. Okay, so when we move those electrons through this, we have a current that is flowing. So that's what I represents. We measure current in amps. So if you've ever heard something measured in amps or amperes, that's what current is. Q represents charge, and we measure charge in what are called coulombs. So when we talk about Coulombic attraction, that guy is what we're talking about, because Coulomb dealt with how charges attract. So coulombs, the unit of measurement named after him, measure the amount of charge. And so charge is just that property that we deal with where something has more or less electrons and protons, so basically ions, or the charge that like electrons and protons carry, okay? And then T is going to be our time, and we measure time in seconds for this. So if we were given minutes or hours, we would have to convert them. We need them in seconds. Now this is basically saying our amount of current, that flows through this is dependent on how much charge there is and how long it flows, right? So the number of electrons flowing, how much charge is flowing, and how long it's flowing tells us its current, okay? Basically that rate, how fast are we getting electrons to move? So one thing that pops up when we deal with this equation and look at problems like finding how much sodium is produced from this is we need a constant that's going to help us go between coulombs and how many electrons we have. So we use Faraday's constant. So this is another way of saying 96,485 coulombs per 1 mole of electrons. And because we can write it as a fraction, we could flip that fraction, we could write it either way, and we can use it in conversions, right? We can set it up in railroad tracks. And then we also know that 1 amp is equal to 1 coulomb per second. So that can help in a conversion as well. So if we're given amps, we can just change the units to coulombs per second. So if I said, hey, I have a 15 amp current going, then I could say I have 15 coulombs per 1 second. It would be the same thing. So those are things that can help us in terms of conversions because we can change things into this fraction form. And anytime we have those fraction forms, we can use them to do railroad tracks, right? To do conversions. So it says this information can be put together typically in a path like the one following. So if I wanted to know this answer up here, the amount of sodium produced over a given period of time, okay? So I could use my time to relate my current and charge together. I could convert from my charge using Faraday's constant to my moles of electrons, right? There's my Faraday's constant. I could use my balanced reaction to find my moles of a particular chemical, so in this case my sodium, and then I could convert to grams of sodium if I need it. It just says amount, so that might be grams or moles or different things. So this shows you a basic setup of how these things connect together. We can start from, any point really and go to any of the others. We just have to keep that order in mind. So we use this as a guide to help us in our calculations. But we're going to just start with that current equation first and do a couple examples with it to see how it works. So I'm just going to copy it down here. I equals Q over T. As a reminder, this is on your equation sheet. It tells you on your equation sheet what I, Q, and T represent, that they are the current and the charge and the time, so you don't have to memorize that. So that'll help as well. So this is saying what is the current, so that's going to be I, of a circuit when the charge, or with a charge of 30 coulombs, so that's going to be Q, over 4 seconds, so that's our time. So just as a little example here, if I wanted to know the current flowing through a circuit, I would take my coulombs, my 30.0, my amount of charge, and I divide it by my time, 4.0 seconds, and I would get my current. So 30 divided by 4 gives me 7.5, okay? And that's coulombs per second. Now, if we remember, up here it said 1 coulomb per second is equal to an ampere. So I could leave it like this, or I can write 7.5 amperes or amps. Both of those would be valid units, okay? Kind of like when we write moles over liters for molarity, or we write capital M, it's the same idea, okay? All right, let's take a look at this one. It says how much charge, so again, charge is Q, is transferred through a circuit with a current of 25 amps, so that's I, and in 160 seconds, so that's our time. Well, if we think about our equation, I equals Q over T, we are looking to solve for Q. So Q is on the top here. That means we need to get rid of T, and it's being divided. So we're going to do the opposite and multiply it. So Q is I times T. So I is going to be our 25.0 amps. And we're going to multiply that by 160 seconds. And that's going to give us our Q, or our charge, our amount of charge flowing through our circuit. So if I was to look at these units right now, nothing's canceling. It's kind of confusing. So 25 amperes, again, an amp, if we look up here, is equal to 1 coulomb per second. So I can replace that with coulombs per second. And when I multiply by 160 seconds, now my units will cancel, and my units make more sense now. So that's a way of tracking that. And I'm left with coulombs, which are how we measure charge. So we've got 25 times 160, and we get 4,000 coulombs. All right. So we can use this equation to solve for any of those three variables. If we wanted to solve for time, just keep in mind how you rearrange your equation. I'd first multiply by time to get that fraction out of the way. Then I would divide by I on both sides to get that out of the way. So time is Q over I, right? These two just switch places. Any equation where you've got this general setup, something equals a fraction, that's something you're solving for, and the bottom of the fraction can switch places, right? It's a quick little shortcut. So that's how it would look if we solved for time. So it says Faraday's constant can be used to convert the charge in coulombs to the number of moles of electrons. So if we had this charge in coulombs, we solved for that, we could change it into moles of electrons using this constant. So that's how we could kind of take another step, right? We could find moles of electrons. And as we've seen in many previous situations, once we have moles, we can relate to many amounts of chemicals through stoichiometry. Right? The balanced half reactions tell us how many moles of electrons are involved in the reaction. So that can take us another step further. So we're going to look at how that works next. So we'll keep this handy as a reference. But let's take a look at an example. So it says a jeweler is plating a tiara with 0.56 grams of silver from an electrolytic bath. So something that looks like this with silver and your object, so this would be a tiara, containing aqueous silver nitrate. So we've got silver nitrate, so silver would have a positive charge because your nitrate is negative, and we're turning it into its solid form, right? Going from the ion to solid. Well, if it's positive there, and I need to have no charge, I need to add something negative to cancel out that charge. So I'd have to add an electron to that silver to make it have no charge, right? Now my amount of charge is balanced on both sides. So that's really my half reaction that's happening here. So it says if the plating happens over 11 minutes, what current is used for the electroplating? Okay, well, let's take a look. This one's relating time and current together. And we've got our number of grams of silver. So if we just tried to use our equation, I equals Q over T, we would be looking for current, so we would be looking for I, and we have time. What we don't have is Q. We don't have the charge right now. So we're going to have to use our mass here to get us to that charge, all right? And we can do that. So here's the first thing, 0.56 grams of silver. Now, what can we always do with grams? We can always change our grams into moles. And of course, I don't have my periodic table handy, so let me look one up. And we'll get our molar mass for silver, which is, everyone I click on doesn't have molar mass. There we go. Silver is 107.87 grams per mole for silver. So we can get to moles of silver. All right, well, let's think about this. We can always refer back to this as well, right? I've got my mass of my substance. I can get it to moles of my substance. Now, what I can do is use my balanced half reaction that I wrote at the top of the page to get to my number of electrons transferred, okay? Because we're trying to get to that charge. Well, charge deals with electrons. So for every 1 mole of silver, I have how many moles of electrons, right? We want to relate this together. Well, it's a mole ratio. For every 1 silver, I need 1 electron. It's a 1-to-1 ratio. All right, well, that gets rid of my moles of silver. Now I have moles of electrons. Let's look at our paper here. I've got my moles of electrons. I want to get to my charge, right? I want to be able to use that equation I have. So I'm going to use Faraday's constant, all right, in coulombs per mole electron. Okay, I want my moles of electrons to be on the bottom. I want my coulombs to be on the top. So if we look at this, 96,485 goes with the C per mole. So 96,485. Again, this is on your equation sheet. coulombs per mole, so in 1 mole of electrons. So now if I solve that, I've got coulombs, I've got charge. So I'm going to put all that into my calculator, 0.56 times 96,485 divided by 107.87. We're dividing by 1 and 1 here, so I'm going to leave that. 500.89. And we've only got 2 sig figs here, so I'm going to just do 500. And I'm going to keep in mind when I do my final answer that I've got 2 sig figs. And now we can plug that in because now we have our charge. Okay, our original thing is asking for current. We're looking for I. So I'm going to just squeeze this in up here since we've got some space. So I is my charge in coulombs divided by my time. My time's 11 minutes. Remember, we need this to be in seconds. So 11 minutes, there's 60 seconds in a minute. So I'm going to multiply by 60. So we got 660 in our seconds. So we got 500 divided by 660. And I would be equal to 0. And we said 2 sig figs, right? We've got 2 going on from our original number here. So 0.76. Okay, coulombs per second are the same as amps. So there is my final answer. Sorry, I didn't give you quite enough space. I also kind of wrote big there. So that's how we could use this equation to kind of connect all these pieces together. All of this we've done before, right? It's just conversions. It's just finding things with the proper relationship, relating them together, and thinking about where we're going with it. And then we're using this equation as our last little bit to get us our answer. And I could have just divided this by my 660 seconds here as well. All right, let's look at another example. This is a multiple choice. So this is how it might be set up if they didn't want you to do all the calculating, but they wanted to see that you understood how to calculate. So the diagram shows the experimental setup used to electroplate a small object. The current of 0.8 amperes. So we've got current, we've got I is equal to 0.80 amps. Is supplied to silver nitrate for 30 minutes. So we've got time is 30 minutes. I can go ahead and put that in seconds as well. 30 times 60 would be 1800 seconds, since that's really what we need. Which of the following equations can be used to calculate the approximate mass of silver deposited on the object? So this is similar to our last one, but in the opposite direction. We can see right now that we have I and T, so we can solve for Q first. Then we would take that value and do our conversions. Instead of doing conversions and then plugging in, we plug in and then do conversions. So let's figure out what Q is. Q would be I times T, so 0.80. Now, even though my question is not asking for the calculation, I'm going to set it up because then I know how everything goes in here, right? And I can just relate them together. Amps are coulombs per second, and I'm going to end up multiplying that by my 1800 seconds, right? Remember that this 1800 is 30 times 60, right? That's how we got that. So right now we've got 0.8 times 30 times 60. So this one has that, this one has that, this one has it. This one doesn't have the 60. They didn't convert properly in letter D. So I'm going to go ahead and cancel that one out. I know that's not my answer. Now, once I had my answer, right, my answer would be in coulombs, some number of coulombs, and then I'd have to convert. So if we looked at this, we're in coulombs, and we need to use Faraday's constant to get to our moles of electrons transferred. So I'd take my Faraday's constant and change from coulombs to moles of electrons. So this is the 96,485 goes with the coulombs per mole of electron. So do any of them not have this on the bottom? This one doesn't have that 96,485, so I can take that out. That gets me to my moles of electrons. Now this is the same reaction we saw up here with the silver. So we know 1 mole of electrons gives us 1 mole of silver. So that doesn't change our calculation. And then 1 mole of silver going to its mass, 107.87, as we already found. They've rounded to 107.9, and we can see that that's on the top there, so we should be multiplying by that. This one's dividing by it, so it's not A. So that eliminates down to answer C. So as I'm doing this, I'm finding the places where it doesn't match, right? And seeing, does my calculation kind of match up with most of them? Because they're not going to have some, something so crazy in your answers there, in your answer options. Most of them are going to be mostly right. They might be missing something like a conversion, or have not put in the constant in the right place, or things like that. Okay? So let's try one more before you do your practice. Okay, so we've seen one where we convert and then we put it into our equation. We've seen one where we use our equation and then we use that value to convert to what we want, because this would give us grams of silver, right? Mass of silver is what we wanted. So let's look at one more. Zinc is used to galvanize metal to protect it from rusting. If you've ever heard of galvanized metal, galvanized steel, galvanized nails, that's all things that have zinc coated on them. So how many grams of zinc can be deposited on a steel plate used in shipbuilding from a zinc sulfate solution when 0.775 amp current flows for 2 days? All right, so we have an amp, we have I, we have a current, we have a time. So what we're looking for is grams of zinc. That's our final answer that we want. So we're going to have to do some converting to get to grams of zinc. So a couple things we can start with. We can remember that amps are coulombs per second. That can help. We've got 2 days here. We're going to need to change those days into seconds. Okay, I'm going to go ahead and set up a conversion for that so you can see how it would look. So this is just like any conversion we do. We want to change from days, and we want to get to the next lowest value or unit. I don't know how many seconds are in a day, but I do know how many hours are in a day. So 1 day is 24 hours. And then I know in 1 hour there's 60 minutes. And then I know that in 1 minute there are 60 seconds. So I can break it down like that. Now, if you did know one of these and could kind of combine, like if I knew in an hour there were 3,600 seconds, I could go ahead and do that. But it's what you know. So 2 times 24 times 60 times 60. And we get 1,728, or excuse me, that's not 1,000, 172,800. All right, and that's how many seconds we have. Now, we do have that current and those seconds, so we can do, find Q, our charge. So we've got 0.775 amps. I'm going to go ahead and write those in coulombs per second because that helps me think about my units. And then we said 172800 seconds. So that allows us to cancel, and I get my coulombs. 0.775 times 172,800. 133,920. I'm going to go ahead and just wait till the end, and then I'll round everything. We got 3 sig figs and everything, so we'll just round at the end, which is fine. Now, we've got some converting to do, right? So in all these other ones, when we've had coulombs, right, or we've wanted coulombs, we've used this Faraday's constant. So I want to change from coulombs to moles of electrons. Again, this is given on your equation sheet, 96,485 coulombs per mole. Coulombs cancel. Now I got to think about my electrons. Well, I get my moles of electrons from my balanced reaction, which they didn't give us, but we can think about this. The zinc is what we're reacting here. Zinc sulfate, sulfate's a 2- charge, so zinc would have to be 2+. So we've got zinc 2+, changing into its solid form, right? Going through that reduction reaction. So we would have to add 2 electrons to make the charge balance. So that means for every, if we want to change from moles of electrons to moles of zinc, for every 1 mole of zinc, I'm using 2 electrons. All right. Now I got 2 moles of zinc. I want grams of zinc, so we're 1 step away. And let's look up our molar mass of zinc, which is 65.38. All right, and that allows us, we can cancel as moles of electrons and moles of zinc, and we can calculate. So I'm going to start with my previous answer here. I've already got that in my calculator. So I'm going to multiply it by 65.38. I'm going to hit divide by 96,485, and I'm going to hit divide again because the 2 is on the bottom. I don't have to use any parentheses then. And I get 45.37. Now, again, our given numbers had 3 sig figs, so I'm going to do 45.4 grams of zinc. So this is another good example of using our calculation to find our coulombs and then using that to convert to get to our mass. So once in a while we see something like this on the AP exam, or maybe in the oh my goodness, can't think of things right now, in the multiple choice. So that might be something, especially if it was given in a setup like this. They might have you calculate in multiple choice, especially now since you can use a calculator in it, but it just depends. So your practice, you've got a little question here on so you're matching the term to the proper label, so galvanic cells or electrolytic cells. So like which one is a power source or needs a power source, which one has a salt bridge, that kind of thing. So doing that and then doing some practice calculations. There's about 5 of them. One of them is a multiple choice to take a look at. So practice that, ask me your questions, and have a great day, guys.